Welcome you all to the webinar on Edge Cloud Collaboration for Big Data System. On behalf of the IEEE Student Branch, IEEE Computer Society Student Branch Chapter, and Computer Science and Engineering Department of Green University of Bangladesh, I'm giving you a gracious welcome. I'm Sayyida Nabila Akhtar. I'm your host for this session. Today we have among us Dr. Muhammad Yusuf Sararuddin Sir, Assistant Professor, University of Missouri, Kansas City, as the keynote speaker of the session. He runs the Intelligence Network System Lab at the same university. His research focus is on distributed computing applied in the areas of Internet of Things, cyber physical systems, mobile computing, and the big data AI systems. Dr. Sarah obtained his PhD in computer science from the University of Illinois Urbana-Champaign and got his master's and bachelor's degree both in computer science and engineering from Bangladesh University of Engineering Technology. Before joining the University of Missouri, Kansas City, he has been a faculty member at Bangladesh University of Engineering Technology since 2004. The station is graced by the presence of the Honorable Pro Vice Chancellor of Green University of Bangladesh, Professor Dr. Muhammad Abdulrazak Sir, as the chief guest. And the station is chaired by our Honorable Chairperson of Department of Computer Science and Engineering, Professor Dr. Muhammad Saifullah Sir. Unfortunately, due to some unavoidable circumstances, Sir could not be present among us today. And I am very pleased to say that today we have among us Sir Asuring Sir, Associate Professor, Department of Computer Science and Engineering of the Green University of Bangladesh, and we would be glad if Sir take over the session from now. Over you, Sir.
Oh, should I start or
Nabila?
Okay,
yes.
I could not hear your last words. So have you called our keynote speaker or?
No, sir. I was handing over the session to our chair, session chair. So it's Asuring sir.
Sir Asuring sir, please.
Okay. Assalamu alaikum. Welcome everyone to this webinar titled Edge Cloud Collaboration for Big Data Systems. By this time, we already know that we have among us Dr. Muhammad Yusuf Sararuddin, Assistant Professor, University of Missouri, Kansas City, and our Honorable Pro Vice Chancellor, Professor Dr. Muhammad Abdulrazak, Pro Vice Chancellor, Green University of Bangladesh. Thank you all for joining this event. I am Sayyid Hassanul Kabir, Assistant Professor, Department of Computer Science and Engineering, honored to be chairing this event. We all know that the value of data and this value will increase day by day. So the biggest challenge now is how to use the data. Big data actually describes the volume of data, both structured and unstructured. Big data can be analyzed for insights that lead to better decisions. Most people know the centralized nature of next step is how to localize data. That's where in the past results have been regarding collaboration to the edge and in order to have much through internet to the speaker Dr. Muhammad Yusuf Sararuddin, Assistant Professor University.
this occasion, and I'm very glad to be here. So today I will be talking a couple of research problems or a couple of works that I did in this space that you just got introduction. So the title of my talk is for Big Data Systems, as it been introduced at the University of Missouri, Kansas City, and I lead a lab that's called Intelligent Network Systems. I take general interest in cloud computing and distributed systems. I'm trying to focus my discussion and tasks into this topic. So of course we are all in the, we have spaces these days. These are instrumented by sensors, by cameras, by acoustic sensors, by all kind of different things to observe our phenomena around. It can be on buildings, it can be on roads, it can be on houses. So, and all these constitutes the so-called Internet of Things, where we have bundle of things connected, capable of computing, capable of generating data. They are connected to the internet, and they produces data for many different applications. And in certain contexts, they all comprise another kind of system that's called cyber physical system, where we have physical objects that are capable of producing sensor data or even capable of processing data. And also we have these computing elements, the cyber element that kind of process those data. And of course, big data is also fueled very much by the proliferation of social networks, information networks, world wave that we see, the bloom of internet, the proliferation of internet and internet-driven services. It's also being proliferated due to the dominance of web applications, mobile applications, media streaming services, audio services, video streaming services, YouTube, Vimeo, all these things. I mean, this is a whole lot of ecosystem beats, and they're all producing one and only one thing, that is data. And data is the de facto generation and consumption at the same time very much of all these computing system that we can think about very much, I mean, these days. And the grand challenge of all these reality is very much, if we can call these kind of this big data systems, and the grand challenge for the whole system is to derive value from data, and to be more precise, is to generate actionable information from data. Data is a raw fact of about things that is happening somehow, and when we aggregate data or we assimilate data and then process on it, then of course we produce actionable information out of it that can be acted upon, that can be realized upon, and that can be taken care into account to applications and depending on the scenarios. So let's take an example. Let's say I have a smart home security systems where a home, standalone home maybe, could be instrumented with multiple cameras around that periphery, so that it can look after who is entering, who is leaving, or is there any burglary events, or is there someone intruding to the house or so, or is there any wild animals gathering or other thing. So it can be many different applications that can be there, that can have this kind of sensing task going on. And all these camera instrumented outside are what they are doing. They are capturing data, of course, and then maybe locally processing it, or at some point will be transmitting these data to a cloud server or a cloud infrastructure where all these data will be get processed in some meaningful way, and then actionable information will be disseminated to homeowners or maybe security officials if there is any incident happen to that particular deployment. So this is a scenario where we see that we have a set of entities where data is being generated through video camera, for example, and then data take a pass to somewhere to get processed. Let's assume this is a cloud infrastructure and a cloud server, and then it get processed for interesting events, anomaly detection, and all these different applications. And then information come back to the user or applications or apps, so where they take action on it. The same scenario can happen beyond home also. It can be happen on smart city context. Let's say smart city is more and more instrumented than normal home, so it has all these different sensors and receptors, information data generators that we can think about. So all these sensors deployed on a smart city context, city roads, city blocks, streets, or maybe buildings. These are all can have camera, can have audio sensors, can have acoustic sensors, can have other environmental sensors, pollution sensors. So all these different sets of data generator can be there, and they're all collecting data, gathering data, and then transmitting all these data to some infrastructure in cloud infrastructure where the data is being processed, and then generate some information out of it, some actionable information per se, and then disseminate them to individual users, end users. It can be human, it can be another machine, or it can be some office. So depending on the situation, that can lead to that. So the centerpiece of the whole thing is that we can think about in a kind of a fashion like this. So we have a scenario where we have instrumented space where things can be observed through predominantly by sensors. So when we say observe, we are flattening out to be sensors, but it can be some other tools also. But someone is generating data, something is generating data somewhere, and then that data is transported somewhere so that that data can be analyzed or processed. And then some other information can be generated out of that processing. And that information can go to someone who can then take an action on it, right? So this is a cycle that we prefer, that we normally call, it's called observe, analyze, act, right? So there's an observe phase where things are being observed. This is a data generation part. And then the data is being processed somewhere, that's analyzed part. And then processed data will be disseminated to users, individual stakeholders, or agencies that will be on the act plane. So if you can extend that out, and this is the drawing that we see, right? So we have observe phase where we produces some data get produced, and the data takes a path in some way through communication network mostly to somewhere where the data get analyzed, right? And then data, from that data we produce, the information gets produced, and then that information is being propagated to other sets of user who then acts on the data. We can put some other verb for the same operation. The observe can be mean sense, can mean collect, acquire, gather. So these are the different terms that we can use in place of observe. The same way when we say analyze, we can say compute, we can say process, we can say infer, we can say learn, predict, all these different verbs that can replace analyze in some meaningful, interesting way. And of course, when you say act, it can be replaced by actuate. That means whenever we would certainly have some machine that can act on the received data. That could be another possibility. It can notify people, it can be notify user or push data to someone, it can deliver, it can disseminate. So this is the kind of a cycle. This kind of more of a broad way how a data system process data. Data get processed, get generated somewhere through some process, observe, and then data make a pass or transfer to somewhere where it gets processed, and then action is taken, something like that. So if we can place exactly where this happens, let's see. So the observe phase, let's see, collect, sense, these are happening by sensors, right? It can be by camera, it can be by microphone. So devices, apps, people, even people can also produce data, of course. So these are the data generation parts. Who are the generators of these data through these observe, collect, sense thing. And then, of course, where the analyze is happening. If in the traditional sense, when you say we need to process a massive amount of data, so that means here the amount of data that we are referring is massively large. So that means it may not be individually capable, individual devices or individual human carried device or individual sensor is not capable to analyze it in place. So it should rather be done in somewhere where normally designated by cloud, right? Cloud is an infrastructure where we can post computing resources to analyze data at very large scale. And of course, when I say what act happens on individual device again, or maybe on actuators, if there is an actuation part. So that means, let's say I want to control traffic based on video feed. So then, of course, the actuation is done through traffic lights, something like that. And then it can be, the actuations can also be happen through devices, people, and application. So the big picture here is that, okay, I have a data generator that's happening in the left side of the drawing. And then those data is being transported to somewhere to get processed in the cloud. And then the cloud generates further information out of those data in the form of actionable information per se. And then another set of information now being sent to end users again, right? So this is the cycle that we can think of. So in this perspective, when we split the entire thing, we say there is an element that you can put between observe and analyze. So observe is the process by which data is generated, and we are transporting entire data to the cloud. But instead of transferring the entire data to the cloud, we can think about some way that there can be some edge device or edge component, some, let's assume some abstract way. So there can be some other extra computing layer can be there that can be in the path of data and then can process things on the way. So that could be another position of what one position, possible position where edge can demonstrate itself. The edge can also place the other way around when the information is passing towards the user after being processed by the cloud. So in that case, we can think about edge computing is a process or is a means by which computation gets closer to data and user. So edge computing is a realization how data can be processed outside cloud, but somewhere in between data generation point and cloud, in both way, whenever data is going towards the cloud or whenever the data is going towards the user from the cloud. So it can be in both way, and then we can define it respectively. So let's assume that if we put edge computing between the data generation point from the observe phase to analyze phase, that means we are computing, we are referring edge computing in the data collection sense. These are data collection system where the effort of the setting is to collect data from field and then get it propagated to the cloud. But before it gets to the cloud, it will be computed somewhere in between. So that's the edge layer between data and cloud. Another way we can think about when the cloud how cloud already processed the data, and now the data is going towards the user for taking actions or for some other purpose, then edge computing can happen on that path also. This is normally, I mean, these can be there many different names we can put to there, but one predominant name given to this kind of setup is called notification systems, where the massive number of users receive data from cloud. So, and there can be systems where that is end-to-end. So that means we have this collection phase, and then collection hits edge computing infrastructure and then get processed in the cloud. And then cloud wants to disseminate the data to the user, and then it goes to the edge again, and then go to the end user. So that's an end-to-end system that can be also possible. So with respect to these two realization of edge, the way we just saw, we can think about two versions of the edge thing, or two versions of edge computing per se. Let's see. One perspective of edge computing we can call it data facing edge. So that means data is being generated by observed phenomena, and then before data is pushed to the cloud through network infrastructure, there can be some computation happen on the way to the data. So there can be, this is called data facing edge computing. And there can be many interesting problems that can arise in this direction when the data is moving towards the cloud. One predominant application or one predominant set of tasks or research tasks, to be more precise, happens. These are the listing of tasks that we can think about. One predominant work is data volume reduction, because we are talking about a collection of sensors. These are massive in number. So they produce data in a very high rate, and they're all going towards the cloud. Let's say you have a video camera installed in every homes, and then they're all collecting data. So if you want to stream all this data back to a cloud infrastructure, then of course it's a heavy volume to transport somehow. So is there any good way to reduce the data as data is progressing, as data is going towards the cloud? That could be another thing. Redundancy reduction is another popular technique that people use. The data, when data is produced at large, there are lots of redundancy in it. So there are redundancy in time, redundancy in space that can happen. Partial processing of data, that can be another task that can happen. Instead of doing all computation in the cloud, some meaningful computation can be happening in the edge part also. So there can be other input, so data upload planning, state estimation, anomaly detection, summarization, aggregation. These are the different tasks that you can think of the edge can perform when the data is going from generation point to the cloud. Similarly, when the data going the other way around, this is called user facing edge. So that means here the data from the cloud is going towards the user, and potentially we have a big number of users because population scale devices. And let's say I want to push notifications to mobile users, and of course there are lots of mobile users out there, and some meaningful computation can happen in that way also. So this we can call user facing edge computing or user facing edge and user facing edge. So what are the interesting things that can happen in this dimension or in this domain? One important thing could be notification generation. So let's say that we want to do a very scalable notification delivery to millions of users or millions of mobile phones, let's see. So this could be an interesting thing. Content adaptation, right? Let's see, whenever content is being disseminated to user, some sort of a change or some degree of adaptation can be made to the content that is being delivered to the user. I mean, content adaptation can be in a very wide sense. Let's see, there can be translation service that can translate content based on the recipient language. Let's see. So this can be done on the user path when the data is moving from cloud to the user. Handling end devices is another interesting task in this domain. One of the biggest tasks that happens in this domain is called handling megafolks. That means the number of people, number of mobile devices, number of mobile apps that you are referring that are receiving data from a cloud is a very big number. So we should be there can be an interesting problem in that domain also. Reliable delivery is another one. So these are the listing of different terms or different problems that can arise in two versions of the edge computing realization. So we did, as in a group, we did a significant number of works in these two particular angle of this edge computing, and we have a couple of publications in them. For this particular talk, I will be focusing on two tasks, to be more precise. So, and one will be on the reduction path. So that means whenever data is going towards how the data volume reduction can happen. That's one problem. Another problem, when the data is going towards the user in the second path, that's in user facing edge, how the content adaptation or content adjustment can happen. So these are the two topics that I will be just focus on for this particular talk. Okay, let me see. I have a question. Let me see. Okay, yeah. So let's see one by one. So for the first one. So it's called the cloud facing or the data facing edge computing. This is the data collection systems, as I just said. Data is moving toward the cloud. So data is moving toward the cloud through edge. So what the edge gonna do? Edge is going to do a volume reduction tasks. Let's see, and redundancy reduction. That's one task we'll be discussing. And the other problem, we said the user facing edge computing. So, and the example scenario is notification systems where the data is moving towards the user. And we'll be discussing one problem that's called Enrich notification delivery. Okay, so let's see one by one. Okay, so this particular task, this particular problem we are going to discuss is called inverse scale. It's for IoT for urban sensing. It's a joint task from University of California, Irvine, Buet, and the National Tsinghua University, Taiwan. So what is this problem about? This problem about urban sensing. So what does urban sensing mean? Urban sensing means that we need to have let's say I have a smart city infrastructure, and then someone perpetuate urban landscape for pollution monitoring, for example. Let's see where the air pollutions are, where the noise pollutions are, where the garbage pollutions are. So all sorts of different pollutions are being monitored and measured by a sensing system, and that sensors are deployed and produced. So for that particular task, we developed a multi-sensor IoT, that's Internet of Things box, that can be deployed in places, in situ sensors, and we call it inverse scale. These are small boxes, just like you are seeing in the drawing. So it's kind of a small box with sensors and computing board. It's mainly powered by Raspberry Pi, and it has lots of gas sensors, humidity sensors, temperature sensors, audio sensors, camera. So these boxes, these are environmental monitoring box, can be deployed in a certain location, fixed with the location, or they can be mounted on a backpack or in a bike, and they can be moving, they can be moved users. So these are normally we call the cloud assisted sensing. So the purpose of this deployment is to observe the air pollution, pollution level in a city, you can think about. And then the overall goal is to build a fine-grained, high-resolution spatiotemporal pollution map, right? So for, let's say I have a large space and where things are happening, and I want to see which areas are more populated, more polluted than others. And I also want to see them as time changes, how that evolves. right? This is normally called a spatiotemporal map of pollution, and we want to get in a very high resolution so that I have a precise understanding of which part of the area is having higher pollution than others. And so to enable this, we build a platform with all these sensors and mostly gas pollution sensors and also camera and other thing. And it's a power, it's a Raspberry Pi driven setup, and it's powered by a battery, because it will be deployed outdoor. And it collects data in a periodic fashion, some periodic fashion, and then collects data stored there, and then passes this data to the server, and mostly in the cloud through a 3G connection, because it's an outdoor deployment. So we don't anticipate there should be Wi-Fi. So it should send the data over 3G connection to a remote server. The problem with this 3G, so that means periodically capture reading and upload data to the cloud, upload all this captured data over 3G to a remote cloud. The problem with this setup is that, okay, this is an outdoor deployment. I need to rely on 3G connection, but 3G connections are expensive, right? Here, you someone need to pay very much per byte, right? So, and every 3G connection in some way or other, it comes with a limited data plan. So the problem is when I have this kind of sensing platform deployed, and if they're collecting data all the time, then how can that data can be transported from that point to the remote to the computing node, respecting the limited data plan. So the challenge was, as I said, the 3G data plan is expensive. The upload bandwidth is very limited. So we cannot send very much whatever data is captured there, because the volume of data that's being captured can be very high, can be way bigger than the data plan that's the platform supports. So that means we only need to upload useful data to the cloud. And what does that useful really mean? Of course, that's what we need to do. We need to check out. And one thing we can do is we can reduce redundancy by some. That's the thing we should be discussing. So there are two solutions that we talked about. We worked on. One is called the prune redundant data on the devices themselves, because the sensors are on the device, and the device, whenever devices captures all this data, it can prune some data, it can delete some data from its own point, and then only upload important, interesting data. That could be another thing. That could be one thing. Another strategy is to reduce redundancy through coordinated operations, so that whenever a bunch of such devices are deployed in an area, they can be coordinated themselves in some fashion, so that redundant data is not captured. Redundant data can be captured, but redundant data is not transported to the cloud, because our data bandwidth is limited. So the controller, we need to deploy an edge controller, as we'll be seeing in a minute, and its controller will decide who is going to sense data and who is going to send data and when. Okay, so the first problem that we said, that we upload data with a limited data plan. So the problem is, given a certain data plan, we need to find a pattern so that we can capture only meaningful information. So the idea is that, okay, let's see, I have a sensor platform and I know a certain data volume that I can upload. How can I capture data so that I can be respective to that? So the key idea is very much simple. The idea is the sensors that has a very high variation in their reading. So that means, for example, a temperature sensor is sensing data, and as we know, the temperature doesn't really change widely, right? It's kind of it doesn't change instantaneously from one point to another point. So whenever a temperature remains constant for some time, then we don't need to sample it in a high frequency. We can delay the sampling, we can delay the capture. But whenever there is a high variation in temperature reading, that means something interesting is happening. So that means I need to sample in a faster rate. So that's the idea here. So, and based on that, so the degree of variation in the sensor reading will designate how frequently I need to be collecting data. So that's the basic idea, and then it all relies into this rate limited upload operation. And that gives us one strategy. The another thing we said is whenever we have these nodes are deployed in numbers, let's say I have lots of such environmental monitoring sensor or monitoring box deployed in a wide area, then we need to coordinate the operation. Why we need to coordinate operation? Because it can happen that I have a couple of sensors deployed in one location, and they can be crowded, right? So it can happen that some individuals in a certain place and collecting data, but another individual is also there. So he is also collecting data, and we are considering a case that the where so that means redundancy can happen in two ways. One is that multiple people are going in one place to collect data, or data collection can be separate in time. So that's the thing. So that means I don't need to collect data from all points from all locations. That's the key idea. But how someone will going to coordinate that? So that's why we need to deploy a computing node somewhere near to the site where this data collection is happening. Let's see, in a city block or in a certain area in a campus. Then we can put an edge controller. That edge controller will take the state of the information, all sensors that are deployed and their current position and what data they are collecting now. State information will be collected, and the edge controller will decide or will coordinate precisely which sensors need to be activated and when. So, and this is called activation plan, right? So this is an activation plan that will be generated by this edge computer node, that's edge controller that will be sitting near to that site. And whenever and as per the edge controller diction, the data will be collected by the sensors, and then those data will be uploaded to cloud. But those uploads will be budgeted, right? So let's see, since we have a data budget that every individual sensors deployed in the scene has a data budget, but you cannot exceed that budget. Let's see, you can only upload 100 megabytes per week or something like that. Then that need to be respected somehow. So the edge controller that is sitting behind that is sitting near to that particular site will going to check that, and then we'll realize that. Okay, so what is the strategy here? Okay, the key idea is called the space-time coverage. Okay, let's see what is the best coverage. Okay, best coverage is that sense data from everywhere, every time, right? So it's a kind of a 24/7 everywhere sensing is happening. I mean, I have sensor deployed in every part of the city, and it's all sensing all the time. Well, that's too expensive, right? Too expensive in both in terms of the volume of data they will generate, and also in terms of the energy and everything that is expended for sensing that operation. So that means we cannot afford having a continuous monitoring all the time sensing. Of course, this gives the best coverage possible, but that's not achievable. So what we need to do is that we can exploit or leverage the spatiotemporal impact. We don't need to sense every part of the space all the time. Why? Because we argue that every sensor reading that is collected from a certain location has a certain temporal impact, and also has a certain special impact. Let's see, if I collected data from a certain street segment, then I don't need to collect from the same street segment for some time, because every data has some value in time dimension, right? Or I have a data collected from a certain point A. I don't need to collect someone else also collecting from the location A, right? Because the data location is already collected. So that means the data collected from a certain time and space point, a space-time point, has some degree of redundancy when the same data is collected from the same nearby time and nearby space, right? So we can think about everything doesn't belong to just a point. Instead, it has a span, and if anything overlaps with that span, that means that content is redundant. So we don't need to collect it. So sensor readings can be collected distant apart in time and also in space. So we need to separate them out, right? Even though we want to cover the entire space, but we don't need to put sensor in every point in the space. We can split them. We can separate them in space and also in time. So that's the key idea here. And of course, this separation and the influence that happens through this separation is dependent on the sensor type. And the goal of this edge controller is to control who is going to be activated when, so that it can maximize the overall space-time coverage, right? And of course, it will be with the subject to the overall data budget, because the volume of data that can be processed, that can be produced is limited eventually. And the goal is to comply that, and also to activate as few nodes as possible. Why we want to activate less sensors? Because if we activate less sensors, of course, we can save energy, because the sensor should not need to run all the time. Okay, so in order to achieve it, what we did is that we did in a space-time partition. Of course, space and time are continuous. Of course, and like any like most other systems, we cannot operate on state, time, and space in a continuous fashion. So you need to discretize it, right? So space is partitioned into cell, as we see from drawing. So that means the space will be partitioned into some cell. So every cell will have a certain size where the sensors will be positioned, and the time will also be partitioned into some segments that we call here time frame. So the time will have frames, and space, the area where the things is happening will be called cells, and each will be remaining one particular cell at any given time frame. Okay, so then we introduce a notion that's called coverage. The coverage means that a certain cell, I have a node where that a collection is happening, right? So if I deploy, if there is a sensor in certain cell and that sensor is collecting data, that means that cell is covered. That cell is covered, of course, obviously, because someone is collecting data from that particular location. But a cell can be partially covered also. What the partially covered mean? Partially covered means that, okay, a particular cell is not covered by any active node, of course, but it can be covered by some nearby nodes. So let's say I have a couple of green dots here, right? These are green sensors. They are located in different cells, and this particular light green cell is not covered by any sensor, but we can assume that this cell is partially covered because there are some nearby cells that are collecting data in that place, right? So I don't need data collected every point, because if I have some data collected nearby, then I can assume that that particular cell, is not fully covered, but it's partially covered. And that can happen with the blue cell, that can happen with the red cell, red cover. So here the green one is one type of sensors, and the red one is another type of sensors, and red one also has some partial coverage, and green one also has a partial coverage. So that's the key idea here. So that means whenever a cell is not covered by any sensor, we can still have some sense of partial coverage, and in the sense that some other nearby cell is collecting the data. And it's not happening only on the space dimension, it's also happening in the time dimension also, right? If I have a sensor reading for this minute, and if I am reading in the next minute, then if I have a need in the next 5 minutes, then I can say, okay, these are temporally correlated or temporally covered. So that's the key idea. That's the key concept introduced here. And we also have another notion is that if we can collect more data from a certain cell, this is always good, right? I mean, let's say I have here you see one of the cell is covered by 2 green sensors. This is always good. If multiple sensor can observe in a certain space, we can have more fidelity of the data. But one thing is to be noted that, okay, whenever we have multiple sensors collecting data from a certain point, it doesn't add linearly, right? It's a sub-additive property, because adding more and more sensor is just adding redundancy to it, right? We don't need to cover the same space multiple times. Of course, it's good, but it's not that good in some sensors. So all these things are blended together to kind of formulate things. So at the end of the day, what we got is that, okay, given this cell information, this time frame information, and device location, and also these impact function that we just talked about, we need to find the scheduler or the edge controller that we talked about. We're going to compute an activation plan for each time frame that we're going to say, okay, which sensor need to be activated at what location and in which time, right? So and the overall objective is to maximize the overall coverage, the space-time coverage of all cell coverage, and then it will also going to maximize utility. So that means whenever multiple sensors collect data from a certain location, utility increases. And also we're trying to minimize active nodes. So how many sensors I need to activate in a certain moment. Of course, if I activate more sensors, they are collecting more data. That means they are depleting their energy, because these sensors are battery powered. So the plan is to compute, or is to determine an activation plan that we're going to maximize all and minimize these 3 metrics, 3 quantity, as we just talked about, subject to that my overall volume of data that gets generated is within the budget that I have. Well, that is technically it's a multi-objective optimization problem, and we try to formulate it as it is. I'm not going into the detail of the equations, but you can think about there are 3 terms here. One is to maximize coverage, and then wants to maximize utility, and also minimize number of active nodes. That's why you see there is a summation of these two terms, and but there is a negative. I need to minus, so we need to put a minus that term. So that means number of active nodes. If we can minimize it, it's better. So we solve it through an algorithm. It's called greedy heuristics. It's a hard problem, in fact. It's MIP. So the greedy algorithm works kind of this. So it starts with an empty plan, so the nothing is activated. So now it kind of finds a node and sensor pair that gives the largest marginal gain in terms of coverage and utility if it needs to activate any new node, right? The idea is very simple. So whenever I'm going to activate a new sensor in any new node, I need to check what is the marginal benefit it gets in terms of utility and coverage. So whoever gives me the best incremental gain, then that node will be chosen. This is a very common heuristics normally done in these kind of hard problems, and we kind of iterate this thing again and again until and unless the volume, the amount of data volume that should be generated is within the budget, and it's still within the budget. We also try to do control strategy so that sometimes even though we exceed budget, the activation can happen because we have some interesting important data to capture, but overall data volume will remain bounded. So then the overall results gonna look like this. So what does it mean? Technically, it says, okay, if I don't prune anything, let's say I let all sensors running all the time, so that means this is the volume of the data they will produce, the black line. The black line is just growing as the number of nodes increasing. So the volume is going high and high. Of course, it's going to exceed our data budget. But if we activate pruning the way I just mentioned through this coordination through an edge controller, then of course the volume of data will be bounded. Even though data, lots of data is being generated, but they will not be all uploaded. Only the important information will be uploaded. Okay. So how do I know that I uploaded only the important information? Because we are reducing all this redundancy. So the right drawing says, so even though we don't upload all this data, but the overall utility of the data is still remains the same. So that means even though lots of data are pruned, but the overall coverage of the whole system or whole map still remains high because it doesn't send all this redundant data beneath, right? That's the whole idea. So that means it's an example of how a distributed coordination near to the location where the data is generated can produce higher value from by stopping unnecessary data uploads to a cloud infrastructure, to a cloud server. And that's the value, that's the one kind of data reduction technique that edge computing can provide, right? So whenever it sees data going towards the cloud, it can access all this redundancy between the data based on certain scenarios, and then it can prune data. But even though the data is get pruned, but the overall utility that we get out of those data, let's see the pollution map, still remains with a very high fidelity, and it's meaning. So that's what the right drawing says. Okay, so that's kind of the work we just wanted to describe in the direction where the data is going towards the cloud, and some redundancy reduction can happen on the way. Okay, so now let's move to the other part of the talk where I said when the data is moving towards the user. Let's see, the cloud infrastructure is there and it's providing data or information, some information or some content towards the user, and then we need to do some adaptation to that. So we can call user facing edge computing, right? So data is moving from the cloud towards the user, and on the way something will be done. Okay, what's that something is? For this particular problem, that something will be enriching notification. So that's what I will be describing now. This is also joint work, University of California Irvine and Max Planck Institute, and also University of Norway. Okay, so this problem is about media content delivery to mobile user. So mobile users, as we all know, I mean, we all are very much, all of us are mobile users, and as a mobile user, we have subscriptions to all these different services, right? We have accounts in Facebook, we have accounts in Twitter, and we also have many many of them has accounts on these kind of streaming services, YouTube, Spotify, and other services. And all these media services, the way they interact with the user, they produce notification for all these events that happen, right? This is called notification for the media content for the mobile user. And now and then we all receive notifications in our mobile phone with a clink sound and saying that, okay, you have something, you got a new friend request, you got a new post, you got a new like, and someone tweeted something, someone retweeted something, some new album is released, some new song is released, some new song is liked by somebody. So these are all different events that are happening in the social media and social space, and the mobile user is going to receive all these notifications. And notifications are mostly push notifications. We should be saying that it's push notifications come to the individual users, and normally bare bone text messages, right? That's what we see whenever a new album is released in Spotify. Let's see, Spotify is a music streaming service. So and where the musics are posted and an online user can listen to them. So whenever, let's see, a new album is released, then user receive a notification saying that, okay, a new album is released, and you go and check. So normally, if these text messages kind of bare bone text messages and doesn't contain any detailed information, so it's really hard for the user to assess well what those content about, and at the end of the day, are they going to be useful to me? So that's the thing that is unknown. So what we wanted to do to avoid that, we need to, instead of just pushing saying, okay, you got something, we need to provide a snippet of the media content with the notification, so that the user can see what that content is. But that will not be the full content, but delivering the full content in the notification is hard and it's unnecessary, because user may not be interested about it. But if you don't tell the user what that content is, then of course user has no other option other than just going to the website and seeing that he's not interested about that particular content. So what is this about, this rich note that we call rich note? It's called rich notification. So what it does, it kind of enriches the notifications with media content in it, or media content sample snippet, right? So let's see, someone uploaded a photo in the Facebook. So instead of saying that, okay, you got a photo, it will put a thumbnail of it and saying that, okay, this is the photo that's got uploaded. If you are interested, then you can go to the real website and can consume it. If it's an audio file, instead of sending the whole file, of course, it will be sending a snippet of it. Let's say 5 second, 10 second, 30 second, 60 second. If it's a video get posted, then it will send a snippet of it. The issue is that whenever I say a small segment of the media content that is being pushed or being notified to the user, that small segment can be different sizes and different presentation and levels that we call normally presentation levels. I can have a picture that can be just 10 by 20 pixel, can be 20 by 40 pixel, can be 50 by 100 pixel, in different pixel resolution. In different resolution it can have. If it's an audio content, then it can be 5 second, it can be 10 second, it can be 30 second, it can be 60 second, and similarly for video thing. So whenever I need to add an media piece with the notification, that media piece can be in different degree of detail. So now the question is exactly how much detail I want to put to the user. There is a catch here, right? So if I want to put a bigger content, then of course it will be expensive. But if I put a very small content, then user will not be able to evaluate whether he will going to interested about it or not. So we need to make a balance between these two. So that's what this rich note does. So what does rich note does? Okay, so let's say I have a media server where the content is being reposited and it's going to be delivered to a user. So what we do is that we deploy edge server in between the user and the media server where the content is coming, and then that edge server will sit in between and will look for every content that is going from the cloud to the user. And before it gets released to the user, it will produce a rich notification out of it, and then we'll put, so let's see the media content is being released, and then it received by the edge server. Instead of edge server saying only you got a new album, it will going to, okay, this is a new album and this is the 5 second preview of it. A song is released and here is the 10-second preview, right? So that's the thing, it will be sent to the user. User will check the notification, and if will play the sound, and if it's 10-second interval music is good, then he will go and download the entire music or listen the entire music, something like that. This is the setting. So So that means it's an edge server that kind of sits in between the content propagation between the cloud and user, and try to adapt the content, try to adjust the content on behalf of the user with respect to that particular user. And the question is which notification I should be enriching. So I should not be enriching notification that is no interest to the user, right? Let's say if user doesn't like rock music, so whenever there is a rock album released, there is no point of sending a 5-second preview with that, right? Because that user is not interested about that content. So why you bother sending a 5-second preview out of it? In that case, you are just exploiting the data budget of that particular user, right? All this message sending with media content is expensive, right? So, but if that user is a rock concert fan, then of course it has value to add that thing. So that's the whole idea. So that means we need to have some way to evaluate the utility of that media sample that we are sending, right? And it should adhere to the user constraint. And then of course it should also maintain that user is running behind user device is running behind a cellular connection, most preferably, and the cellular connection has data budget, just like the way we saw before, right? That means I will not be able to send everything that I have to send, right? There should be a compromise between how much data budget that particular mobile device has. And of course, it also depends on the energy budget of the device also. So battery levels and other information that can be taken into account. So the edge server that is sitting behind will be in between this communication between the mobile user and the media content server, and we're going to adapt the content on behalf of the user, and will deliver only the meaningful information to the user in the form of this rich notification. So the central question is to how to evaluate the utility of a certain content. And we take an approach that's called utility driven approach. Okay, so it has two components. So what I mean, it's kind of it's a little bit abstract in some sense, utility of notifications. So we define utility of a certain content has two part. One is called content utility. Content utility means absolutely how relevant this content is to the user, right? To the particular user. If the content is not at all relevant, then there is no point of enhancing it, right? Because enhancement will just cost the user, but will have no value because user doesn't take any real interest in that particular thing. And another part of the present utility is called presentation utility. So what does mean? That means, okay, if I decided that, okay, I need to put a 5-second snippet, or I need to put an album thumbnail for that particular user because particular user is interested about it, then how big the presentation should be, right? Should I be a low resolution picture or a high resolution picture or bigger, or should I be sending 5-second preview, 10-second preview, 15-second preview? Of course, if you send more, then of course it's a high value, but of course that will be high expensive also. So that's need to be assessed, and we just need to combine them together somehow. So the content utility is the utility that kind of gives the content utility, how relevant the content is. Normally it is dependent on freshness of the content and who posted the content, who likes them, what is the social rank of that content and everything. And normally it is learned from historical data, and we need to train a model out of it. So some AI model that can predict whether a particular content will be interested to a certain user or not. And presentation utility is orthogonal to that. This is the richness of the presentation. So how valuable a 5-second preview versus a 10-second preview versus an 11-second preview. This is subjective. This is unfortunately, this is subjective because people has different taste and different response patterns in media content. So what do we need to do? We need to make a survey out of users, in fact, to get an idea exactly what is the presentation utility is. So the key idea is that given these two utility, we can the simple function to incorporate them to is to multiply them together, right? If the content utility is high and presentation utility is also high, then of course natural utility will be high. If any of them is low, then of course the utility of that particular piece content will be low also. So at the end of the day, this boils down to a notification selection problem. This is a multi-choice knapsack problem with this structure of formulation. And now, as we know, the multi-choice knapsack problem is NP hard. So normally it's we try to solve it through multi-choice knapsack heuristic. So the key idea is that we always take items in a descending order of a gradient, and the gradient is determined by utility getting divided by size changes. So that's the idea. So we did an experiment with this thing with audio content, as you're saying, and we got this data from Spotify with a non-disclosure agreement with them, and it is done a trace-driven simulation. So that means we will be mimicking user behavior by running and store trace out of it. And the way we measure content utility is through a classification problem. It's a machine learning model that is constructed from Spotify data, 6 million user notifications data. It was a random forest built with 100 forest and with accuracy of 0.7. Accuracy is not that high though, because all users has a very wild variation in their music choices. So it's really hard to come up with a very consistent model or very high accuracy model. And the presentation utility, we did we did a survey on user, asking user to how they evaluate a certain content duration, 5 second, 10 second, 15 second, and so. And based on that, we produce all these utility metrics that we just showed, and then try to come up with, if we want to enhance or enrich a notification when it's going towards user, how much richness we should be putting in. Okay, so the results look like this. So, and of course, it depends on user budget. So here the drawing that says, okay, what is the budget of that particular user? If we increase the budget, that means user can have higher budget. That means cellular communication budget. That means it can go higher enrichment, right? So that's the thing we are showing. And what we wanted to show is that when we add notification enrichment, it's better than any fixed choice. Right? Let's say I receive every content, and then every time I send a 10-second preview. Okay, sending 10-second preview will just going to deplete the battery, and we're also going to deplete the data budget, right? So that's not going to work. So that's what it shows here. So that means overall utility of rich node is higher than any other constant choices. That means I don't enrich notification. But if and another version is that I don't send any enrichment at all, I just send the metadata. The problem with metadata is that in that case you don't receive any utility at all, because you don't have a chance to consume the content. Instead, whenever you receive a notification says, okay, someone released an album, someone need to go to the website to see the content even before he decides whether he's going to consume that content or not. So that's the thing. So, and similarly, in the right drawing, we show how things are mixed up, right? It's not necessarily the case that all notifications are sent with a certain degree with a fixed presentation detail. It is not. Sometimes 5-second preview is more preferred than 10-second preview, sometimes 30-second, 50-second, and it's all over. And as you see, that whenever data budget increases, there is a tendency to allocate more and more segments. So that's the thing. So the rich node is an example of an edge computing framework that kind of intercept data as data is coming from the cloud to the user, and then do some adaptation on top of it, and make higher utility of those content consumption by the user. Okay, so that's kind of the two problems that we want to discuss. So in that whole perspective that we saw, we can think about edge computing the way we discussed, is that, okay, I have an end users or users and devices, right? Let's see in two examples. In one example, we have the sensors who are collecting data, and the second problem that I said, rich node, where I have mobile user who is consuming content. So they are all nothing but an end user. We can think about some end devices. This is our periphery of the thing, and then in the center we have this cloud. The cloud is the one who is sitting and hosting all this computation and content. Data is generated by the devices, is going towards the cloud, or cloud has content just like the music content, and then content is going towards the user. So users and devices are in the outer periphery of the ring, and the cloud is sitting in the center, and edge, the thing that we just discussed, is somewhere in between. It's kind of a wrapper between cloud and edge, as cloud and end user, right? And edge computing means that we need to put this computing node in between these two entities. And of course, it's a span. So the whole purpose of this edge computing, this edge computation, extra computation that is happening on the way to user or on the way to the cloud from the sensor or from the devices, is to bring computation closer to data and user. That's the overall objective here. And as we said, the edge can be on the path on the data path as data goes towards the cloud. So that means you can have it, we can think about a path that is data is going from the devices to the cloud, or the other way around. So cloud already has content that has been posted somewhere, and then that content is being delivered to the user. So edge can sit in that path also. So that's the two flavor that we talked about, right? It's a cloud facing edge or data facing edge, and cloud and the user facing edge. So that's the thing. And this kind of scenario is coming more and more and more and more prominent and dominant in the context of Internet of Things and big data and AI applications. And of course, it has different specialization. Exactly how this edge computing can be leveraged depends on applications, application and certain scenario. We just saw 2 examples, but of course there can be lots of other examples possible. And if we can see the whole thing in a kind of a more holistic way, this is the way we can think about. So let's see our end happens. So this is a word, this is kind of a thin west glass model where we can think about all kind of data producer are in one end, who kind of produces all this data for us. And then there can be data consumer, that's the user, that are also sitting on the other part of the other of this glass, right? So in one end there is a data producer, and in another end we have this data consumer where the data is going. And let's assume that all the data is going towards the cloud, and data is also coming from the cloud. So the cloud is kind of sitting in the center, and we can envision this edge that we just talked about is somewhere in between these two, right? So data facing edge is sitting between data producer and cloud, but user facing edge is sitting between cloud and user. So that's the way we can kind of think about. And this is a new layer of computation. The way we have cloud computing, maybe edge computing is just another layer of computing layer around that spectrum. And this is the predominant concept that is coming towards these days. And so it's a new reality. It's an extension of edge computing. I mean, people can say about it's an extension of cloud computing, but more so it's more towards the edge or towards very close to the end user. And it can be anywhere. So and technically it can be anywhere between end and cloud, as we can see from this drawing. And this is all referred as end edge cloud continuity. It can be continuously somewhere in between, from the end devices to the cloud, right? To be more precise, it is anything outside cloud. Okay, so why this kind of reality is coming into? Well, it's and one relevant question here is that where that edge be, right? It's an open question. It's an open question these days. So we can say that okay, I can do some processing in between my data and cloud, but where should I be placing it, right? Who is going to host these services for me, or should I be deploying a server? And so normally its placement is an issue, and computation, what computation should be happening at the edge versus what computation happening in the cloud. It's really an issue. It depends on cloud, how remote the cloud is. Usually that's the case when we say that cloud is far away from end users. So some computation need to be happening to the edge, to the user or to the data generator where the data is being generated. So normally in terms of who is going to host these computing resources or computing services, there are 2 players in the market. One is called telco operators. Telecom infrastructure is one suitable location who can implement this edge infrastructure at their network. Cloud provider can also be another player that can provide these edge computing resources. So they can extend their cloud onto edge. That's normally referred as mobile edge cloud or edge cloud. I mean, this is another term. 5G, the evolution of 5G that we are seeing, and it's evolving through this time, and it's coming towards, and it's being realized in many countries. 5G enables its computing in certain way. Well, one example is that 5G allows to deploy server or containers at their cell tower base station by this network virtualization and other techniques. And of course, the future will be future more and more edge computing phenomena will be there. And then we can think about scenario, there's a multi-tenant edge. That means multiple application or edge resources can host multiple applications and across multiple users, and similar to cloud infrastructure, right? The way cloud infrastructure is shared across a wide set of users, edge resources can also be shared across a wide area, wide set of users. That is becoming a reality. And of course, at some point, intelligent edge will evolve that will mostly going to host the AI workload. And this is particularly interesting for AI driven workloads, because for AI thing, if all the computation need to happen in the cloud, then someone need to host all data to the cloud, but that's just too expensive in certain scenario. So that means somewhere in between, we need to get them processed closer to where the data is being generated. So, and that is very relevant for AI workload, right? So artificial intelligence, machine learning, deep learning, as they are becoming more and more prominent, then edge computing will also get prominent. In those cases, the edge computing will going to provide this model as an inference service, or model as a service, or ML, machine learning as a service like thing. In that case, we deploy or we train a model in the cloud. Let's see, because training is expensive, training will going to happen in the cloud. But whenever that model is deployed in the scenario, then that can be done very much on the device. Sometimes is not very capable to run deep learning models because they are big and resource hungry. So they can be done on edge computing sources. It's not entirely on the end device, but it's somewhere close, but a little bit of higher capability. So that could be a new reality with the emergence of AI and machine learning and deep learning. Edge computing is going to become a very center attention. Okay, so with that, I'm going to end, and thank you all for listening to me, and I will be happy to take some questions if you have. Thank you very much.
Okay.
Thank you, sir.
Thank you, Dr. Mohammad Yusuf Sarawaddin, for such an informative speech delivered with such clarity. It was really informative and thought-provoking. So we'll now be taking questions. So audience, if you have anything you would like to ask our keynote speaker, now is your chance. So you can raise your hand, unmute yourself and ask question, or you can drop question in the chat box. So Navina, I'm requesting you to conduct the question and answer session.
Yes, sir. Dear participant, feel free to put your questions if you have any. And I'm sure Sir will accept question in Bengali too.
Yes, sure.
So please feel free to ask your question.
যে কেউ প্রশ্ন করতে পারবে, যে কোনো প্রশ্ন যদি থাকে।
Now, I had a question.
Sure.
So I was wondering with my small brain that if you told about two constraints. One is minimizing the active nodes, and other one is the coverage. My question is,
Okay.
If I minimize the active nodes, then if there will be any conflict between the area coverage.
Yes, you are right. I mean, this is a very good question. Thank you. Yes, you are absolutely right. So if these are two conflicting goals, right? So that means I am reducing number of active nodes, but I also want to maximize coverage. So that means if you cannot achieve them both, but the whole thing is to try to make a balance between it, right? So I can active more and more. I can activate more and more sensor. Of course, that will be better. Will higher coverage, but that will be also coming at the cost, right? Because they will be all producing data and they will be all depleted their energy. So it need to be a right balance between it. And of course, these are all two contradictory goals, right? So that's why it has a multi-objective optimization. So our intention is to maximize in one direction and also at the same time somehow reduce in another direction. And making a balanced decision between the two is the whole idea of the optimization framework that is trying to achieve with this goal in mind. Yeah, you are right.
Thank you.
It can happen. I mean, if let's see, if coverage is essential, let's see, I don't have any activation in a certain location and I need to make a coverage. So then of course, even though it kind of activates a new node, there is no other option other than activating it, right? But if there is already some node working there and I am already having some coverage, so just to increase my utility, I may not activate a new sensor there, because in that case, I'm just activating a new node. And of course, but the value that I get out of it, it's not that heavy. It's just too marginal, right? So that's the balance under the hood it kind of tried to get. Yeah, I think you are right. This is a very
Okay, sir, got
good
it, sir.
question.
So our respected teacher, Monul Islam sir, wanted to say something.
Okay, sure. Okay, yeah, let me see. Question, thank you so much. Oh, I want to cover. Oh, okay. So I see a question. Maybe I can read that out. Thank you very much. It was very informative. So actually, I wanted to ask if I want to cover all over the world with one cloud, is it possible? How is possible? Yeah. Well, it's not, right. So for example, if you wanna, cloud is very elastic, and of course it has virtually infinite capability. But of course, it's not, one cloud cannot serve all, right? Of course not. I mean, so that means the computation need to be distributed in certain way. That's the whole idea of edge computing. So instead of pushing all data, instead of sending all data towards the cloud and doing all computation in the cloud, that is not economical, that is not scalable in some sense, and that is not even required, right? We can distribute data, or we can distribute this computation onto other nodes, so that other computing node can also do the operation on the way. So it's not that cloud is going to do all computation at the end. So let's assume that I have a smart city infrastructure, and I have lots of camera deployed on streets. And so if every street send their video data to a remote cloud all the time, then it's going to be a huge amount of data need to be transferred. But you don't need to, right? We can deploy some computing node in nearby locations where they will intercept the video, is do some simple processing on the way, and then send the process data or filtered data to the cloud, so that the further processing can be done. So and how you're going to connect the edge? Of course, this is an interesting issue, and this is an ongoing issue. Who is going to provide these services? Let's see when we say cloud infrastructure, we know that, okay, there are certain companies, and so we have network infrastructure, they are computing nodes, and they have a data center where you have server machines, and you can connect to them, right? But for edge, nothing like that exists yet. But there are systems coming in, and many cloud vendor these days, Amazon, Azure, Alibaba, and Google, they have built their own edge infrastructure, and they are building it, in fact, and it will be coming more and more. And in that case, the way we connect to cloud, maybe similar fashion, one day maybe will be also cloud connect to edge node also. Edge node is also being deployed or developed by edge computing infrastructure, is developed by telecom operator also, right? So telecom, mobile phone operator also wants to provide edge computing services in their infrastructure, so that instead of hitting a long path towards the cloud, you can do processing very close to the radio network. So that's the idea here, and there are certain literature in that direction that says it has a very high value in that way. Yeah, that's a good question, in fact. Thank you.
If any other question have from the participant side.
Okay, let me see. Thank you very much. Okay, thank you.
It look like no one have any more question.
Okay.
Okay. So thank you, participant, for your questions, and thank you, Dr. Yusuf, for answering their questions.
Okay, thank you very much. And I'm glad that I was here, and thank you all for listening to me.
Thank you. So now it's my pleasure to welcome our chief guest to today's webinar, Professor Dr. Muhammad Abdul Rajab, Honorable Pro-Vice Chancellor, University of Bangladesh. He has a vast experience in this field. So now I would like to request Professor Rajab to deliver his speech. Professor Dr. Muhammad Abdul Rajab.
Thank you very much, Sadar Salkovich sir. I was very carefully listening to Professor Yusuf Sararuddin, who is a very close colleague to us, and I'm really impressed to see that from the very beginning, he was talking about the applications first, and why do we need uh, large scale computations to materialize those applications, and what the traditional computing system is, and what is the necessity of edge cloud. I believe our students who participated here have got uh, a lot of ideas, concepts, starting from the very fundamental, the necessity of edge cloud for enabling many real-time applications up in this area. Well, I also noticed that he concentrated in this talk on uh, reducing the volume of data and reducing the data redundancy. Those are definitely very important problems in this area. And some of the techniques here highlighted on uh, how to prune data efficiently. He explored uh, controlling the sensing interval. That's a very important controlling knob for collecting data from real life fields. And definitely, he also talked about coordination of operation for collecting the data. When a huge number of IoT devices are deployed in a certain scenario, then they can also coordinate to each other to reduce the data collection from the field to the cloud repository. And one of the most important problem in this area is to study the spatio-temporal relevance, the relationship of data. Sometimes some of the data values are highly related to some other data values, so they need to be collected within the stipulated time. That has also been focused. And I also interestingly see that he mostly avoided complex algorithms related to ILP or so, but he nicely introduced greedy heuristic solutions so that the computations can be made within the polynomial time. Uh, I also see that he nicely integrated the utilities related to content and related to presentation and made a single utility. And this utility maximization problem has also been uh, made considering the very important constraints related to the user device battery as well as the user data budget. Those are very much important as well. So before the students, already some of the research problems have been introduced by our keynote speaker. And this field is really uh, uh, getting mass interest from many researchers from different corners of the world. Uh, I basically concentrate on quality of service and quality of experience issues, issues related to allocating resources to enable the computation, issues related to how can multiple ASICs collaborate to each other to increase the quality of experience of the users. Some other problems related to solutions that focus on minimization of energy expenditure of the user devices. But some other approaches are also recently coming related to use of the various machine learning and artificial intelligence techniques to virtualize network functions. And when the network functions will be activated and when they will be in the sleep mode or in the uh, uh, wake up mode. That is another important research problem related to efficient resource utilization of those is clouds. So this is really interesting and important, and I believe this talk has helped our students a lot. Maybe for some of you, it was a bit difficult to understand the inner meanings and the operational processes of the system. But I'm sure these things are not but that much difficult if you start reading the text in the literature. You do have access to IEEE digital resources from the computers of your university. So you can easily download the fundamental resources related to this. Start with magazine papers, but then it's with very simple conference papers, and then when you will get a good level of idea on the basic operational processes, then you can go into the go for the transaction papers. And I see the keynote speaker himself has a good number of publications, reported publications, starting from conferences to transactions and networking. We really feel proud of intelligent and very impactful researchers like him. And definitely many of you have the capacity to reset his stage someday in future. So you keep confidence on your capacity and continue your study, SARS and research, so that you can uh, explore some of the interesting problems and get solutions out of that. And definitely will be able to publish good research papers out of your results. So with this hope and some message, and again thank you to Professor Yusuf Sararuddin for his valuable time. I know it's late night in United States. So thank you very much, the keynote speaker, the audience, the faculty members, and my dear students for being here to listen Professor Sararuddin. Thank you.
Okay, thank you very much for inviting me. I really enjoyed talking. And if you have any questions, just send me email. I will be happy to respond.
Thank you, sir. Thank you, Honorable Professor, for your nice speech and suggestions and guidelines. I believe our students will follow your instructions. Now, I would like to thank you, all the participants joining in this webinar and make it successful. Especially, I'd like to thank our chief guest, Honorable Professor. Your presence always inspires us. I would like to thank our keynote speaker, Professor Dr. Sarwar. Thank you, sir, for joining and delivering your speech despite of a very busy schedule. It is really informative, interesting, and thought-provoking. And now I would like to also thank all the participants, IEEE Student Branch, Green University of Bangladesh, IEEE Computer Society, Green University of Bangladesh Student Branch Chapter, Department of Computer Science and Engineering, Green University of Bangladesh, our today's anchor Nabila, and all the participants and those involved in making this webinar. Thank you all. And I hope it has been beneficial and inspiring for you as it has